Hey, let's start. So the test is on Wednesday. The test review answers there are now posted. So if you go to that sample test link on the Blackboard page, you can find the test review answers. So I hope you've had a chance to look at the test review. Maybe you did with John on Friday. And John will be also available after class as usual today, right? In South 405 for another opportunity to ask questions or look at this test review. But the answers are posted now. But now be sure that you look at the test review and try to go over the test review before you look at the answers, right? Okay? So if you haven't had a chance to go over the test review yet, try to go over it first on your own without the answers, and then look at the answers, because if you are just looking at the answers simultaneously to looking at the test review, that's going to give you a false sense of security, okay? So so be sure you look at the review first, try to go through it. It's not that long, and then work on the and then look at the answer second. But we're going to look at a couple of problems from the review today, just to remind you of a couple of things for the test. Okay, coming up on Wednesday. So on your homework, then homework 3.2 is due at the time of the test. I moved that back a little bit, but it's due at the time of the test, so that's not due at midnight. So be careful about that. That's due at the time of the test. So you need to finish this one before you come to class on Wednesday. So I had it due originally tonight, but you need to finish it before. And the homework on marginal analysis, since we're just talking about some of the things that are in that homework today, and I don't think most of the problems, the harder problems on this homework are not on the test, then I postponed that one until April 2nd, which I think is Saturday. So you really don't have to be finished with this one by the time of the test, although it'd be good to look at it before the test, depending on how much time you've got. But the test review, this one you've got to finish, and the test review you should definitely do prior to the test. Now, for all of that work, you do get a reward, okay? Of course, your intrinsic reward is all of this knowledge that you're gaining, right? Okay, so you have that reward, but which is the most important reward. But you have another reward also, in that we will not have class Monday, okay? So there will be no class Monday, April 4th, all right? Okay, so no class Monday, April 4th, right? So you don't have to come the Monday following the test. I'll be out of town, so I haven't posted that announcement yet, but just remember that. I'll say that again next time. But so no class next Monday, so you don't have to get up early, maybe, unless you have an 8:30 class next Monday. Okay. All right. Let's look at. We're going to look at maybe a couple of problems from this homework, and then a couple of things from the test review. And then a little bit about marginal analysis, the final piece there that we're going to do. So you can work on this marginal analysis homework. But let's look first at the test review. Okay. So I didn't bring any copies of the test review. If you have a copy of the test review with you, that's great. You can pull that out, but I'm going to project it here anyway. Okay. So again, if you haven't looked at this and printed this, be sure you do that prior to. Wednesday, and the answers are posted on the Blackboard page under the sample test link. All right. So this very first question is really pretty easy. Okay. It says. The daily revenue for Dino's Dog Biscuits, okay, is given by that formula, 6x minus x squared. And in that formula, X is the daily demand. Demand always means the amount sold, the quantity sold. And this is in hundreds of pounds. And the revenue is measured in hundreds of dollars. So the output from this function is in hundreds of dollars. The input here is also in hundreds, but hundreds of pounds, okay, of these dog biscuits, okay? So here you're just given an expression, and then, so very typical type of question for this course, you're just asked to interpret it. We have lots of questions like this on the 3.2 homework at the end, okay? So it says, suppose you're given that R prime, so you've got to be very careful now on the test and watch the function notation, right? This is not R of 4, but this is R prime of 4 is equal to minus 2. So that means the rate of change of the revenue, right? That's called the marginal revenue function, right? And so the marginal revenue, x equal 4, is minus 2. Interpret this value in the problem context, okay? So I made this one kind of easy because it's just to fill in the blank, okay? On the sample test, later on at the very end of the sample test, you have a question about marginal profit as opposed to marginal revenue. It's this question, 7D, okay? So this is marginal profit. That means P prime. Remember, that's the archaic notation for the derivative. In this case, it's the derivative of the profit, okay? But here they're just asking you to interpret, but not giving you a template, right? So in this problem, you'll have to fill in all of the whole sentence there, all right? But in this first one, a little bit easier, you've got just to fill in the blank, okay? So it says when the daily demand is, so in this expression, what's the daily demand? 400, right, okay? So it's 4, right? But remember, it tells us here X is the demand in hundreds of pounds, right? Okay, so when the daily demand is 400 pounds, all right, okay, then the daily revenue is it's either going to be increasing or decreasing, right? Because this is marginal revenue. So in this case, the marginal revenue is negative, right? Okay, so that tells us that the revenue is what? Yeah, decreasing, right? So the marginal revenue decreases, right? Okay, and now we have to get the unit of a measure correct here, okay? Well, the output of the revenue was hundreds of dollars, right? Okay, so that means that the daily revenue is decreasing by $200, right? Because we're told the marginal revenue is minus 2, so that means that the daily revenue is decreasing by $200, and then and it's always per unit of input, right? So a unit of the input here, a unit of the demand is going to be 100 pounds, right? Okay, 1 unit of input here would be 100 pounds of dog biscuits. Not 1 pound of dog biscuits, but 100 pounds of dog biscuits. So you could just write in there 100 pounds. Yeah, and then when you look a little bit more closely at that, you can say, well, if it's $200 per 100 pounds, then we might as well just say it's $2 per pound, right? So you also could have said here $2 per pound, and that would also be correct, all right? Okay, $200 for 100 pounds is the same as $2 for 1 pound, right? Okay, so either way you express it there is okay. Yeah. Mm-hmm. What now? No, here you have to write 400 pounds. Yeah, definitely 400 pounds right there. Yeah, okay. So the only reason we can simplify this one is we're thinking, well, that's $200, right, divided by over 100 pounds, right? $200 per 100 pounds, and that reduces to just, $2 per pound. Yeah, but the original 400 pounds, you have to keep the same. Well, there is an expression involving the marginal revenue, okay? Here it's asking us what actually is the marginal revenue formula. So how did I know that r prime of 4 was equal to minus 2, right? I mean, I just told you that, but how did I know that to be the case? And I got that from the marginal revenue formula, right? Okay, and that's easy to calculate because we know the revenue formula here, right? So r prime of x is going to be, and all we have to do is just find the derivative of this simple expression, right? Well, that's an easy one now for us to find the derivative of. We don't have to do any really work using our differentiation rules, right? What's the derivative of 6x? 6. And the derivative of x squared is going to be what? Negative 2x, exactly right. Okay, right. Just bring the 2 down right in front as a coefficient, and then subtract 1 from the coefficient, so that's going to leave you with x to the first power. So you have 6 minus 2x. So indeed, when you plug 4 into that formula, right, you get 6 minus 8. That's where the minus 2 came from, right? Okay, so that's why that expression was, that's why this expression was correct, right? Why that equation was correct. Okay, so 6x minus 2x, there's the actual formula for marginal revenue. All right, now it says, last part here of problem number 1. So it says a very simple cost formula here. It says the cost of producing X hundred pounds of dog biscuits is given by this formula. Can't get a much similar cost function than this one, x plus 3. All right, okay? So write the formula for the profit function, right? So if you know the revenue formula and the cost formula, which is x plus 3, then you can easily write down the profit formula. Because remember, profit is just revenue minus cost, right? Okay? Revenue is the amount you generate, right, from selling an item. Cost is your cost of producing an item. Well, you take your revenue minus your cost, and what's left over is going to be your profit, right? Okay, so P of x there is just r of x minus c of x. So r of x was 6x minus x squared, and c of x was x plus 3. Be sure you subtract off now the entire expression x plus 3. So put it in parentheses there. Don't just write minus x plus 3 without the parentheses, because you'll get the sign of the 3 slightly incorrect. Okay, so and when you simplify that, you get 6x minus x will be 5x, right? And then we have the minus x squared, and then a minus 3. Okay, a minus 3. So there's the formula for the profit. All right. And remember, the marginal profit, which is not asked for in this question, but the marginal profit is the rate of change of the profit. Marginal cost is the rate of change of the cost. So the marginal profit is going to be whatever the rate of change of the profit is, right? Which is 5x minus x squared minus 3. So that's going to be 5 minus 2x, because when you take the rate of change of 5x minus x squared minus 3, well, the rate of change of 5x is 5, the rate of change of x squared is 2x, and then the rate of change of that constant minus 3 is just 0. So here our marginal profit formula is 5 minus 2x, which, by the way, is, that's always the same as the marginal revenue minus the marginal cost. Okay, so marginal profit is marginal revenue minus marginal cost, right? Because if you take the rate of change of r of x minus c of x, you're going to take the rate of change of r of x, which is r prime of x, that's the marginal revenue, minus the rate of change of c of x, that's the marginal cost. Okay, I keep emphasizing that because that's going to come up repeatedly in the homework. Marginal profit is marginal revenue minus marginal cost. All right, so suppose we wanted to know where the profit, this is not asked for in this problem, but suppose we want to know where is the profit maximum. Where is the profit maximum? Okay, so if you think of a graph of this function, if you just visualize a graph of this function, that's going to be where you have a turning point, right? Okay, where the profit is maximum. If you sort of draw a, if I can find a pen here. Keep hitting all my pins. Huh? I can't draw a picture of it. Maybe I can. So if you just visualize here a picture of the profit, all right, right, that profit is going to be maximum at a turning point, okay, right? It's going to where the profit peaks out is going to be a turning point, and that turning point is going to have what sort of tangent line? Horizontal, right, okay? It's going to have a horizontal tangent line there. So we would be led to believe that we could find the maximum profit. We could find the maximum profit where the tangent line is horizontal, or in other words, where the rate of change is what? 0, right, where the rate of change is 0. So the way you typically, okay, the way you look for where a profit is maximum is to look for where the rate of change is 0. Where here is our rate of change of our profit, it's 5 minus 2x, right? 5 minus 2x. So take that rate of change and set it equal to 0, okay? And just figure out what x value will give you rate of change 0. So you just have to solve this equation, 5 minus 2x equal 0. And that's a very easy equation to solve, right? That's just 5 is equal to 2x, or x is equal to 2.5, 5 halves, right? So that would be our candidate for where the profit is maximum, okay, when x is 2.5. So we're thinking, if we can produce and sell 250 pounds of this dog food each day, okay, that is what will lead to maximum profit. If we produce and sell more than that, that's going to diminish the profit, or if we produce and sell less than that, that's also going to diminish the profit. So this would be our goal for sales and production of this dog food would be 250 pounds per day. Okay. I'm not actually going to make a graph of that. Not actually going to make an actual graph of that profit function, but we're thinking if we did make a graph right there at 2.5, that's where the profit would be highest. Okay. This one is pretty easy. This next one, number 2, so I'm not going to go through that one, but all you're asked to do in number 2 is to sort of fill in the blanks in this average rate of change table, okay? So wherever there's a blank, just fill in those blanks, and you can see on the answer sheet what the correct values to fill in the blanks are. What you're really looking for, of course, is this last column of values, right? Okay, because those are the ones that are going to help us estimate this limit, right? We're trying to find the limit as as our increment h here goes to 0 of this slope. Remember, this is the slope of secant lines, and the slope of those secant lines are going to become progressively closer to the slope of the tangent line, and it's the slope of the tangent line, right, that's the same as the rate of change. So that's what. So we're looking for the values in this last column to help us answer what is this limit, and then what is this rate of change at x equals 1. I'll fill those values in for you here. This one turns out to be minus 0.7, okay? And the last one here turns out to be, if you do it with a lot of decimal places, turns out to be minus 0.9997, right? So it looks like, according to that last column, right, what's happening to these slopes as our increments gets close to 0, it looks like those slopes are getting close to what value? -1, right, okay, and that's in fact correct. So this limit is really -1, okay? that limiting value is minus 1. And so that means the rate of change at 1 is, at least our estimate for that would be, our projection for that would be minus 1. Okay? What? No. No, it's a rate of change, so it can be any value, right? Okay? Like, for instance, in the prior example, right? In the prior example, that rate of change of that formula at 4 turned out to be negative 2, you see. Okay? So rate of change can be any value. Okay, now here's the one that's gonna drive everyone crazy. Okay, so this is the one you have to be very careful with on the test with your algebra. All right, so you really need to practice this one. Okay, you really need to practice this one from the review. All right, so let's get it started, but I'm not going to go through every step because I want you to finish this one on your own so that, again, you'll have some, make sure that you practice this a little bit before you come to take the test, because we will have a problem like this one where you need to evaluate a limit in order to find a rate of change formula, okay? All right, so here it's couched in a stated problem, but the stated problem part of this is not really important so much for this limit, okay? So it says the total cost in hundreds of dollars per producing these T-shirts, okay, it's X thousand T-shirts, is given by this formula. So that's a cost function, okay? The output is hundreds of dollars. The input there is thousands of T-shirts. And it says simplify this expression to show that the marginal cost, in other words, the rate of change of this cost formula, is 2x plus 2. Now, you can easily tell that from your differentiation rules, right, that the rate of change of x squared plus 2x plus 1 is going to turn out to be 2x plus 2, okay? So you know that's correct, but I want you to show, going through the steps of this process, to show why that is correct, okay? We can apply the rules to see, the differentiation rules to see that what this rate of change formula is, but now let's use the actual formal limit definition to see why that rate of change is 2x plus 2, okay? So this is just really a bunch of algebra that we have to manipulate here to get at that final correct answer, all right? So let's see, we want the limit as h approaches 0 of c of x plus h. So you just plug x plus h into your cost formula. So you get x plus h squared, right, plus 2 times x plus h, and then plus 1. So see, everywhere you see the x, right, you're going to plug in x plus h. Yeah, I just did a little bit of that. Oh, what was number 3? Yeah, I skipped that one, right, yeah. Okay. Yeah, we're not going to do the whole sample here. Yeah, so there's some more practice for you. This one's a little bit easier because here you're not finding the rate of change formula for this function, which you know is 3, by the way. You can tell that from your differentiation rules. Here you're just trying to find the rate of change at the input 2. Okay, right, okay, yeah. But here we're trying to find the rate of change for any input x at all, right? Okay. All right, so we plug x plus h into our formula for x, right, into our cost formula for x, and then we subtract off the cost formula. Here, the one mistake you're likely to make there is make sure that you put that cost formula, when you subtract it off, make sure you put it into parentheses, right? Okay, you've got to subtract off the entire expression. So if you leave off the parentheses, things will go badly awry somewhere in the future here in trying to simplify this expression. Of course, the denominator is real easy to simplify because x plus h minus x is just going to be h, right? Okay, so the x's just cancel, and you can reduce that denominator to just plain old h, right? Okay, so let's keep writing that limit, because we won't evaluate that limit until the very last step, right? So x plus h squared, that means x plus h times x plus h, right? So don't forget, when you square this, you've got to multiply it by itself, so you have to do it the hard way there. And then 2 times x plus h, that's easy. That's just 2x plus 2h plus 1, and then minus x squared minus 2x minus 1. I'm going to distribute now that negative sign through those parentheses, right? So change the sign of all the terms in the parentheses, all of that divided by h. And now I have to multiply out the x plus h times the x plus h. So that's x squared plus hx, x times h is hx, h times x again, so there's another hx, and then h times h is h squared, and then plus 2x plus 2h plus 1 minus x squared minus 2x minus 1. So at this point it looks really ugly, but see, at that point now things start looking up, right? Because now a bunch of terms are going to cancel. So if you've done this correctly, you should get a lot of terms canceling. So you get x squared minus x squared. So those terms cancel, right? So yay. And then we get what? 2x and minus 2x. So those terms cancel. And then we have a plus 1 and a minus 1. So those terms cancel, right? And so it really doesn't look nearly as intimidating as it did before. You have 2hx plus h squared, and then don't forget that 2h right there, plus this 2h, right? All of this divided by h. And I think now from that point on you can finish it, right? Okay? Because what nice happens here? Well, you look and see, oh, gee, h divides into all of those terms in the numerator, right? H divides into 2hx, and h divides into h squared, and h divides into 2h. So I can divide out the h in the denominator, and so I won't have the h in the denominator anymore. And then you would think about, okay, what happens as h gets close to 0? What's going to happen to that expression? What's it going to end up looking like as the h gets really, really tiny? And it turns out, oh, it looks like 2x plus 2. So you'll arrive at this. This will be your final answer, of course, 2x plus 2, because you already know that that is the correct rate of change formula, right? So when you're finished here, you should end up with 2x plus 2. Now, don't try to fool me on the test and start making a bunch of algebra mistakes and then all of a sudden write down equal 2x plus 2, okay? Right? Because I will, because see, you know what the final answer is supposed to be, right? Okay? So I will know if you've cheated a little bit there and skipped some steps and just wrote down, the final answer is what it's supposed to be, okay? Even though you haven't gone through the steps right, okay? So just saying, don't try to game me there on the test. All right. Now let's look at the part B of this, which really doesn't have much to do, well, I guess it does have a little bit to do with the part A, all right? So it says, suppose you were given that C prime of 1 is equal to 4. That's correct, right? Because C prime was of x was 2x plus 2, so if you plug 1 into that formula, you would get 2 times 1 plus 2, which is 4, okay? Right? So this is correct. C prime of 1 is equal to 4. So it says, interpret this value in the problem context. So this is just like interpreting marginal revenue, except now we're interpreting marginal cost, okay? But the interpretation is quite similar. So notice this is marginal revenue, this is marginal cost, not total cost. If you wanted to know what the total cost for producing, let's see, this was, how many t-shirts is that? That's 1,000, right. So if you wanted to know the total cost for producing 1,000 t-shirts, you would use the original total cost formula, right? Which was x squared plus, what was it, x squared plus 2x plus 1? Yeah, there it is right there. So, so 1 squared plus 2 times 1 plus 1 is equal to 4. Oh, that's also equal to 4, right? So that's interesting. Okay. So the total cost was $400 for producing 1,000 t-shirts, okay? All right? So that's total cost. By the way, what's the average cost for, so the total cost for 1,000 t-shirts is $400. What is the average cost of each t-shirt if you produce 1,000 t-shirts? So yeah, so the total cost was $400. What's the average cost for 1,000 t-shirts? Yeah, that's what I mean. Average cost per shirt, right? Okay. So what's the average cost here? So how do you calculate average cost? That's pretty easy, right? You take your total cost, right, which was how much? 400, right? And divide it by what? By the number of t-shirts produced, right? So you get what? 40 cents? So if you're going to produce 1,000 t-shirts, your total cost is $400, but the average cost per shirt is 40 cents, okay? The average cost per shirt is 40 cents, right? Because the total cost was $400 and you made 1,000 t-shirts, right? So you take your total cost, 400, divide it by the 1,000 t-shirts, and you get 40 cents, okay? So each t-shirt is costing you 40 cents to make if you make 1,000 of them. All right, so what's our interpretation now of the marginal cost for 1,000 t-shirts? So how many t-shirts are being produced here? Yeah, so when 1,000 shirts are being produced, right, the total cost is it increasing or decreasing? It's increasing, right, okay, because again, that's positive. So the total cost increases by, okay, well, let's see, that's going to be $400 per 1,000 shirts, right? Okay. $400 per 1,000 shirts, but you can simplify that and say, let's see, if it's $400 per 1,000 shirts, then it's what? Yeah, 40 cents a shirt, right? Okay. So that's interesting there. At 1, okay, the average cost and the marginal cost turn out to be the same, okay? But that won't always be the case, all right? This is just an example of that. What now? Oh, yes, yeah. Oh, yeah, you can use a note card, right? So just like before, you can use a note card, okay? Right. So, but don't forget about average cost. There's a few problems in the homework about average cost. Average cost is just your total cost, right, divided by the number of items you produce, right? Okay. Marginal cost, though, is something different, right? That's how fast the total cost is increasing or decreasing. Okay. So average cost and marginal cost, not the same thing. All right. We're doing pretty good for time here. Okay, so let's look very quickly at the last problem. So here we're given a profit function, all right? So not cost, not revenue, but profit. But remember, you can, if you know the revenue and you know the cost, you can determine the profit just by taking the cost and subtracting it from the revenue, right? But here that's already been done. We're given a profit function. This is for Benny's beach sandals, okay? And again, we're measuring the demand here in, this is daily demand. This is hundreds of pairs of sandals sold, okay? And the profit is measured, in this case, in hundreds of dollars. Let's skip over A, because that one's pretty basic, all right? That's just interpreting function notation. That's not rate of change. That's just interpreting function notation. So you know how to interpret function notation. You can read the answer off the answer sheet. The second one's a little bit more interesting. Not much, though. This is still not calculus, though. It says, what are the break-even points for these sandals? Okay? So a break-even point is when the profit is exactly zero. When the profit is exactly zero. When your profit is zero, that means you're not losing money, but you're not making money, right? Okay? So it's important to know when you're manufacturing an item, right, how many you have to manufacture and sell to break even. Because you certainly don't want to be losing money, right? You'd rather be making money, but you certainly don't want to be losing money. So let's see, what are the break-even points for Benny sandals? Well, break even means the profit, here's the profit, right, is going to be exactly zero. So just take your profit formula, and set it equal to zero. So we do that all the time. We take functions and set them to zero, okay? And we end up with an equation to solve, okay? So in this case, we end up with a quadratic equation to solve because the unknown here, x, is squared, right? So this is the profit. We're going to make our profit zero because that's when we're breaking even. And we got to see how many of these sandals we have to produce and sell per day in order to break even. So I've got to see if I can solve this equation. Now, you can always solve this equation by using the quadratic formula. But that one's a little bit messy because the coefficients are kind of big. But it turns out this one can also be factored, however. All right. Let me show you. Actually, you can factor this one. I'm going to show you to solve this equation. So I'm going to put the x squared term in front. So I'm going to write that as minus 2x squared plus 25x minus 50. So just write the terms in descending order. And then, since I don't like having a negative leading coefficient, I'm going to factor out a minus sign here. So I'm going to factor out a minus 1 just so I can make this leading coefficient positive. So that will give me 2x squared minus 25x plus 50. Okay? So I want to really look at the 2x squared minus 25x plus 50 and think about that and not worry so much about that minus sign because that makes things a little bit confusing. Okay? So I can't erase the minus sign, but I can factor it out. And now let's think about the 2x squared minus 25x plus 50. And that actually factors. So you probably wouldn't think that, but that one will actually factor. So we have 0 is equal to 2x and x, because that's the only way you're going to get 2x squared, right? If you multiply 2x times x, that's the only way to get 2x squared. And then to get the 50, I think you use 5 and 10. So I think put a minus 10 here and a minus 5 here. Yeah, that will work, right? No, because it's plus 50 in the parentheses. Remember, I factored the minus sign out. Okay? So I want to factor this so I get 2x squared minus 25x plus 50 because I factored the minus. That's why I factored the minus sign out. So minus 5 times minus 10 is plus 50, and then minus 5x minus 20x is minus 25x. So I will get the middle term right, and then 2x times x is 2x squared. So it does factor, and now you can just set the factors equal to 0. You can forget about the minus sign now and just set the factors equal to 0. So either 2x minus 5 is equal to 0 or x minus 10 is equal to 0. So there are your two break-even points. Either x is 5/2 or x is 10. So if you manufacture and sell 1,000 of these pairs of sandals, or 250, this is 2.5, 250 of these pairs of sandals, that is where you're going to break even. Why I left the negative there? I really could have erased the negative at this point since this is set equal to 0, but I just didn't want to show that step, so I just left it there. Okay. No, the answer is 5/2 or 10. Yeah. Okay. Right. So if you manufacture 250 sandals or 1,000 pairs of sandals, then your profit at those two levels will be exactly zero. Okay, so you won't lose money, but you won't make money. So you've got to manufacture and sell at least 250 per day to make money. Okay, but if you manufacture and sell 1,000, turns out you're going to be losing money. Okay, at that level. So I'm guessing the maximum profit is going to be somewhere between these two things, right? Okay, somewhere between 250 and 1,000, because those are the two break-even points. All right. Now let's find the marginal profit. So that's easy. What's the marginal profit going to be? That's just the rate of change of the profit, right? So what's the rate of change of this formula? So now you don't have to evaluate the limit. You can just use your differentiation rules. So what's the rate of change here? 25 minus 4x, right. So part D is saying evaluate that. That means the rate of change of the profit. So that's the marginal profit. Okay. And this is that archaic notation. It's saying evaluate that when x is equal to 6. So what is the marginal profit when x is equal to 6? So if I plug 6 into this formula, I will get what? 25 minus 24? So that would be what? 1. Yeah, so the rate of change when x is equal to 6 turns out to be equal to exactly 1, which is just 25 minus 4 times 6. Right? So how do we interpret that? Right? When how many sandals do we sell here? 600, right? So when we sell 600 pairs of sandals, and this was daily profit, right? So when we sell 600 per day, right, the profit is it increasing or decreasing? Yeah. The profit is increasing by, it's not increasing too much, right? By what? $100 per, how much there? Per 100 pairs, right? Okay, so per 100 pairs. Remember, the input here was measured in hundreds of pairs, right? So when we sell 600 pairs of sandals, the profit is still increasing by $100 per 100 pairs. And so you could simplify that a little bit, because if it's $100 per 100 pairs, then the profit's going up by what? Yeah, $1 per pair, right? Okay, so anytime we sell, if we're selling 600 pairs, right? Anytime we sell a little bit more, we're going to increase our profit a little bit. So the maximum profit is not 600. It does not occur when we sell 600 pairs, right? Because the profit is still going up if we sell a little bit more than 600 pairs, right? What now? The first part of this part? Yeah, that you could just write down as 1. That's fine to write 1. But in the interpretation, you have to explain what the 1 means. Okay? No. It is $100 per 100 pairs. Right, okay? But when you think about that a little bit more closely, $100 per 100 pairs is $1 per pair, right? Okay. Still? Okay, right. All right, so look, we know, so we're thinking, okay, maximum profit is not when I'm producing and selling 600 pairs, because if I manufactured more, my profit would still be going up, right? Okay, but I can't manufacture and sell as much as I want, because when you get up to 1,000 pairs, what's happened to your profit? It's gone down to what? Yeah, your profit is back at 0. Remember, that was a break-even point, okay? So this is not, so the maximum profit is not when we're selling 600 pairs. I wonder where the maximum profit really is, right? Okay, so how do we look for that again? You're going to look where the rate of change is 0, okay? So look where the marginal profit is 0. That is where the profit function will have a horizontal tangent. That is probably where the profit is going to be maximum, okay? So how do we find where the marginal profit has a horizontal tangent line? Set it equal to 0, that's right. So what was the marginal profit? There was the formula for it, 25 minus 4x, right? So just take your 25 minus 4x and set that equal to 0, okay? So when we set the original profit function to 0, that told us the break-even points. When you set the marginal profit to 0, that is where you're going to find where the profit is maximum, okay? All right, so you see the difference there? When you set the profit function to 0, that's where we found the break-even points. But when we set the marginal profit to 0, that's where we're going to look for the maximum profit. Well, that's an easy equation to solve, right? That one doesn't require any factoring. What's the solution to that equation? Just x equal what? That says 25 is equal to 4x, or x is equal to, divide both sides by 4. So you get what there? 6.25. Ah, okay. So that's my suspicion there, okay, that the profit is going to be highest when x is 6.25. So that tells us the profit is not highest when we're making 600 pairs of sandals a day and selling them. The profit is highest when we're making how many? Pretty close to 600, but actually 625, right? Okay. So if we make and sell 625 pairs of sandals today, that's when our profit will be the highest. Okay. So that's how you can answer the last part there. Okay. What's the maximum profit? Well, just take that 6.25 and plug it into your profit formula. Okay. So we think the profit is maximum when we're selling 625 pairs a day. Okay, plug that into the profit function and see what the maximum profit actually is. It turns out to be, when you plug that into the profit formula, that turns out to be $2,812.50. So there's our maximum profit. All right, that occurs when we sell 625 pairs of sandals a day, but our maximum profit is $28,12.50. Got that just from plugging that into the profit formula. Ooh, let's try that one again. Let's try something like that again. All right, but I'm going to do this in the let's go back to the note. So we're going to look at a slightly different example. Okay, so remember last time we were looking at profit and cost and revenue for selling Girl Scout cookies. Okay, and we had a cost function for manufacturing those Girl Scout cookies. It was kind of a complicated cost formula here. All right, there's the cost for manufacturing and selling Q million boxes. We were using Q as the input variable here instead of X. So there's the cost of manufacturing and selling Q million boxes of Girl Scout cookies. And we were just assuming that we were going to be able to sell the Girl Scout cookies at $4 per box. So there was our revenue formula, was just 4 times Q. That's the quantity. Okay. So that's how much revenue we would generate from selling those Girl Scout cookies, and subtract off the cost, and that gave us our there's our profit formula, okay, for the manufacture and sell of those Girl Scout cookies. Okay, so that's about where we had gotten to last time. There's our profit formula for making and selling Q million boxes of Girl Scout cookies. And so we were wondering then, okay, how would I find my maximum? How would I find my maximum profit? All right. Well, now y'all know the secret. Okay. So now you know the secret for finding the maximum profit, because you're going to look for what? Where the marginal profit is what? What now? Zero, right. Okay. So you're going to take your profit, your marginal profit, not your profit, but you're going to take your marginal profit and set that to zero. Okay. That's where you'll look for where the profit is. That's where you'll look for where the profit is maximum. Okay. By the way, if you set your original profit function to zero, what are you going to find? Okay. See, there's the profit function. So if you set that to zero, what does that give you? Yeah, that tells you where your break-even points are. Okay. So if you set your profit to zero, that's going to tell you where you're not making any money. You're not losing any money, but you're not making any money. All right. That would be kind of a tough equation to solve because you've got your variable cubed here. Okay. So kind of a tricky equation to solve. But that's what you'd be looking for if you set the profit to zero. Okay. Are the break-even points. But I don't want to find the break-even points. What I really want to find is where is the profit? Where is the profit maximum? All right. So that means we're looking for where the marginal profit is zero. Okay. All right. So last time we found the marginal profit function here. Okay. And there it is. All right. So there was the derivative, the rate of change of our profit function. Right, so if you don't believe this, go back and just check that. Okay, you can check that using your differentiation rules. There's the marginal profit. Okay. All right. So again, what am I going to do to find where that profit is maximum? I'm going to take that and do what with that? Set it to zero. Right. Okay. So we're going to take that and we're going to set that to 0. And then we're going to try to solve that equation. Okay? So take your marginal profit, set that to 0, and try to solve that equation. Ooh, that's going to be kind of a tricky equation to solve because what kind of equation is that? Begins with a Q. Yeah, that's quadratic. Okay? So that's a quadratic equation. And you can always solve quadratic equations by using the by factoring, maybe, right? Okay, but it doesn't look like we're going to have much luck factoring this one, right? Because we're not going to have much luck factoring that one because that one has these ugly coefficients in it. So if we can't factor, what's our plan B? Yeah, we're going to use the quadratic formula. Okay, so we're going to have to remember the quadratic formula and plug these coefficients into the quadratic formula. And so let's remember what those coefficients are. So the A coefficient here is minus 0.69, and the B coefficient is minus 1.96, and the C coefficient is 1.3. Okay, so I'm going to have to plug those into my quadratic formula and do the arithmetic. Going to be kind of ugly, but it's not terrible. All right. Did y'all write down those coefficients? Because I've got to remember them. Actually, let me copy them. So let's take those and plug them into the quadratic formula. So I have the quadratic formula here. And there are the coefficients that we're going to be using. Okay? All right, so you're going to have to help me do some of this arithmetic. Now, I used, there's the quadratic formula, but remember, we're solving for the variable q, so let me write q instead of x. All right, so what do we plug into our quadratic formula there? We have minus b, so that's minus 1.96, right? And then plus or minus, right? And then we have the minus 1.96 squared minus 4 times a is minus 0.69 times c is 1.3, all of that divided by 2 times a, so that's 2 times a minus 0.69, okay? So that looks a little bit formidable, but with a calculator, not too bad. So minus a minus 1.96 is plus 1.96, right? And then the square root of, all right, y'all got to help me now with this arithmetic. So what's minus 1.96 squared? It's close to 4. 3.8416. Okay. And now I've got to get this a second term here. So be careful about the signs now. So you have minus times a minus, that's going to be plus, and then this is a positive 1.3. So I know that's all going to turn out to be positive. Okay? I just don't know what the value is. So what's that value? 4 times 0.69 times 1.3. $3.588. Somebody else get that? That sounds reasonable to me. And now be careful about the sign in the bottom, okay? So be careful about the sign in the bottom there, because that's negative. All right. Well, I can do this one, I think. So is that minus 1.38? Is that what that is in the bottom? Did I do that right? All right, now we have to calculate, add these two terms together under the square root and then calculate the square root, okay? So that's 1.96 plus or minus, and what's the square root of that, of this quantity, this sum? 2.7 something probably. Am I close? 2 point what? 2.7257296. Can I round it off at 3 there? All right, close enough. Minus wow, this is coming out really not what I was expecting. But times 1.3, did that come out to be 3.588? Let's double check our marginal profit and make sure that we got that right. I didn't check this beforehand, but no, that looks like the correct. That looks like the correct marginal profit. now let's try simplifying that. So you're going to end up with two values there because you've got plus or minus here, right? Okay. So you're going to end up with two values there. One of them is positive and one of them is negative. But the negative one is not meaningful to us, okay? Because remember, this is a quantity of items that we're producing, so we don't care about the negative one. So that one we can throw away. The only one that we're interested in here is the one that turns out to be positive. So what two values do we get there? .55. So about .555, something like that. And then what's the other one? Negative 3.395. What now? 3.395. I'm thinking the signs are reversed here. So what did we? What mistake did we make here? Let's look at a graph here, because I've got a graph. So if I can get it to come on. Well, neither one of them look right. There's the oh no, yeah, one of them looks about right. So there's the profit graphed, okay? That's the revenue minus the cost. So there's the graph of the profit function, right? Okay. And where does it look like where does it look like that has a horizontal tangent? Right there, okay? So that should be where the marginal profit is 0, right? Because that's where the rate of change is going to be 0. So that looks like at about 3.4, right? Okay. So that's where we should have come up with an answer is about 3.4. So it looks like I've got the signs reversed there in my example. Because I think that is this answer here, okay, which should be positive 3.4, and this one should be negative. So where did I?
If you divide that negative 3.395 over negative 1.38, that'd be a positive number.
Yeah, well, yeah. This is no. These calculations are correct, I think, but I've got one of my signs off here. So did I write down? I'm thinking I wrote down the marginal profit wrong. Last time, minus 6.9. Oh, there it is. I did write it down wrong. Okay. You see the mistake that I made? Uh-oh. This is a mistake that you're likely to make too. Okay. When I subtracted off the cost, okay, when I subtracted off the cost, that was a negative 1.96, right? But I was subtracting off the cost. So that's a minus minus, which is supposed to be what? That's supposed to be plus, right? Okay. So that should have been plus. And then, let's see, I should have had 4 minus 2.7, which would have been, no, that would have been positive 1.3. Okay? See, 4 minus 2.7 is positive 1.3. So I made a sign mistake in my B coefficient. Okay? So that should have been plus 1.96 in the marginal profit. Okay? Well, I wish all mistakes were that easy to catch, because all that's going to do here in my quadratic formula is make this a positive, and so when I'm going through the calculations, this is going to be a negative, that's going to be a negative, and so indeed that's going to switch the signs. Okay, so this is going to be minus, I think, and that one is going to be plus. All right. Okay, so indeed, this negative one is meaningless to us because you can't have a negative you can't manufacture a negative quantity. So there is where our profit is going to be maximum when our quantity is when we manufacture. How many is that? 3.39 million. All right. So when we manufacture 3.39 million, that's what leads to the maximum profit. And that's what we saw in the graph here. Okay, because there's the graph of the profit function. There's the graph of the profit function, and indeed, see, that has a horizontal tangent right there at 3.4. I think if I point at that, see if we can get it to. Yeah, there it is. Okay. Exactly 3.395. Okay, that's where the tangent is horizontal. And what is the maximum profit? Well, it's 6.509. Okay, so our maximum profit apparently is about $6.5 million is going to be our maximum profit. Okay, that's what I get for not checking my examples beforehand. Okay, so again. To find maximum profit, your general scheme is to look for where the tangent line is horizontal on the profit function, and that is going to be where the marginal profit is, marginal profit is 0. Okay. All right. Let me leave y'all now with starting one more example. Usually, in that prior example 3, we just assumed that we could sell all of the boxes for $4 a box. Okay, so everything we produced, we assumed we were going to sell it at $4 a box. But that assumption is a little bit unrealistic, because usually what happens is when you're selling items, of course, when you increase the price, what happens to the demand for an item that you're selling? It goes down, right? Sure, right. Okay, so almost all items have that property, right? As the price goes up, the demand is going to go down, or vice versa. As the price goes down, the demand will go up. Okay. For some items, when the price goes up, the demand drops very rapidly. Okay, so these are items that people really don't have to purchase. All right, for items that people do have to purchase, when the price goes up, the demand will go down, but it won't go down quite as drastically. Okay, well, I don't know if people consider Girl Scout cookies are really a necessary item or not. Okay, so probably for Girl Scout cookies, when the price goes up, the demand is really going to go down pretty rapidly, right? Okay, if you price those Girl Scout cookies too expensive, you're not going to sell any of them. All right. So usually you have an equation that you can use to relate the demand and the price, and that's called the demand equation. So here's an example that I've just invented for this example for the demand for these Girl Scout cookies. Okay. All right. So in this example, in this demand equation, P is the price. So this is in dollars per box. And Q is the demand, in millions of boxes sold. All right, so just to get comfortable with this equation, okay, let's think about here. How many are we going to, if this equation is valid, how many boxes will we sell when the price is $2 per box? So what do? That's easy. Yeah, you just plug 2 in for the price, right? Okay, so if the price were $2 per box, just plug 2 in there for the price, right? And you get a demand of what? Well, 12 minus 4 is what? That's 8, okay? So if this demand equation is correct, if we price these at $2 per box, we could sell 8 million boxes. On the other hand, if we raise our price to $4 per box, then what happens? Well, exactly what you would expect, right? The demand is going to go down, and in this case, how much does it go down? Well, so what's the demand at a price of $4 per box? It's only 4 million, right? Okay. So if you raise your price to $4 per box, according to this equation, if that equation is valid, then your demand is going to go way down, right? Okay, people just aren't going to pay $4 a box for the Girl Scout cookies, right? Or not as many people are going to pay $4 per box for the Girl Scout cookies for your demand. So your demand goes down to 4 million. So first, let's answer a couple of simple questions. What price will completely shut off the demand? 6. That's easy, right? Okay, so that's easy to see from the formula. All you have to do is set your demand to 0, right? And just solve for what that price is, okay? So what price will lead to 0 demand? Just solve this equation, right? Just plug 0 in for the demand and solve, and you can do that even just by inspection. It's easy to see there that 2p is equal to 12, right? Or p is equal to 6. So if you raise the price to $6 per box, essentially you're not going to sell any cookies, okay? Nobody wants Girl Scout cookies that bad that they'll pay $6 per box. On the other hand, what's the most Girl Scout cookies we could sell? So that's my second question. What's the most Girl Scout cookies you could sell? I mean, some people aren't going to buy Girl Scout cookies no matter how you price them, right? Okay? Some people just don't like Girl Scout cookies. So what's the maximum number of cookies we could sell?
11. No.
So how can we answer that from our equation? Well, you're going to get to the maximum demand by doing what again? What? Lowering the price, right, okay? So let's imagine if we set the price to 0. Of course, we're not going to really set the price to 0, right, okay? But if we plug 0 in for the price in that formula, what do we get for demand? So remember, you have the demand is 12 minus twice the price. So if you just imagine plugging in a price of 0, then what do you get there? 12. That tells you that no matter what you do, you're not going to sell more than 12 million boxes, okay? I mean, there's just no way to lower the price enough that you're going to sell more than 12 million boxes, all right? So the maximum demand is only 12 million, okay? The most you could sell at any price is 12 million. All right, now, if this, one more thing, if this is the equation that relates price and demand, then what would our revenue formula be? Okay, so what would our revenue formula be? So, see, in the prior example, when we were determining the revenue, we just assumed, well, we could sell the boxes at $4 per box, okay? But in this case, the amount that we sell is determined by the price that we choose. So if we choose a smaller price, we'll sell more. If we choose a if we choose a smaller price, we'll sell more. If we choose a higher price, we'll sell less, right? Okay? So how can we write down a formula for our revenue based on that demand equation? Well, again, in general, how do you calculate the revenue? It's the amount that you sell, right, times what? Times the price per box, okay? But now let's think. What is the price per box going to be if we sell Q boxes? So let's solve this equation for P. So I'm going to subtract 12 from both sides. So that's minus 2P. And then divide both sides by minus 2. So you get P is equal to Q minus 12 divided by minus 2. So if you simplify that, you get 6 minus 1/2 times Q. Okay. So what that tells us is that if we sell this many boxes, that's what our price has to be to sell that many boxes. Okay. So that's what you can plug in for P in your revenue formula. Okay. See, to sell Q boxes, this is what you're going to have to charge to sell all those boxes. All right. So in your revenue formula, just plug this expression in where you have your price. So that's what I'm going to plug in for P. So I get Q times 6 minus, let me write the 1/2 as 0.5. And now when you multiply that out, what do you get? 6Q minus 1/2 times Q squared. There is your revenue formula for making and selling Q million boxes in this version of the problem. Okay. Now you're back to where we were in the previous example. To find the profit, just take the revenue and subtract the cost. Okay. All right. This is the marginal analysis that's in the marginal analysis homework, and that's not quite on the test. Okay. So the test will look like the problems on the sample test on Wednesday. All right. Sorry, we're done. Somewhere. Where's the roll sheet?